section H6 sliding off an ice hemisphere. This problem dates back many years. I encountered it in Holiday on Resnick. I was teaching Holiday on Resnick with the third edition, which had a nice green cover. And I had studied with the blue cover, the second edition, and they had this cool problem with the boy on an ice mound sliding off the ice mound. Let's go ahead and draw a little picture here. So we have an ice mound. Think of that as a hemisphere. And there's a child that's sliding down and going to go flying off it. So here, this is the angle theta, and here there's a radius, capital R. And the question is, find the height where the child goes off. Now, the child starts at the top and basically nudges herself or himself so that the slide begins, and at some point they leave the ice mound. So we want to find what this height is the question. So what we will do here is look at the key idea of when you leave the ice. There's no normal force. You're not feeling the ice press on your body. So if I were to make a nice little force diagram here, and the force diagram I'm giving you here is going to be for this point right there. So they're the two axes there, and here if I drop straight down, alternating interior angles, that has to be theta, which I remember from Zorro. You see that? Isn't that cool? Alternating interior angles. These angles, by the way, are equal also. Isn't that nice? Okay, so here we got mg going straight down. That means this angle here is theta, and we have the normal force going up. I will pick plus this way because that's going to be toward the center of the circle for circular motion. And the equation in that direction is mg. Now I want the cosine of theta minus n is equal to ma, which is mv squared over r. Now I don't need the other equation because, see here, this is going to be 0, where the ice doesn't press on you anymore. That's when you leave. That's when you leave the ice hemisphere. So this gets us immediately mg cosine of theta equals mv squared over r. Now I need another equation with v to get rid of that v, and that's going to be the conservation of energy. So we'll look at 2 points. Point 1 would be at the top, and point 2 will be here, right when we slide off. So the kinetic energy at 1 plus potential at 1 is the kinetic at 2 and the potential at 2. Now at the top, you're at the height r, straight up. So there's no kinetic energy because you're at rest. You're going to nudge yourself. So this is mg r. Then at the second point, you are moving 1/2 mv squared, and this is mg h. But I notice that h here, if I take this triangle and just blow it up a little bit like this, that this is h. There's your hypotenuse is r. There's your angle. So h is r times the cosine of theta. So I get two equations. This first equation, mg cosine theta, is mv squared over r. And then from this equation, I'm going to get mgr is 1/2 mv squared plus mg, and h is the r cosine theta. And as my good friend from grad school would like to bracket pairs when he was working with equations, I will do that. He was a plasma physicist, became a plasma physicist, and married someone from Asheville after she had him as a TA, but after the course was over. Okay, so here what we're going to do is make these equations look nicer for use. And I'm going to multiply the top one, both sides, by r, and this one by 2. So I'll go ahead and bracket these again. mgr cosine theta is mv squared, and then 2 mgr is mv squared plus 2 mgr cosine of theta. And now I can plug in, see this here, these are the same, so I can plug this in right there. And now I get to have one equation. 2 mgr is equal to mgr cosine of theta plus 2 mgr cosine theta. Now it's time to cancel some things. This is amazing. The mgr is going to drop out of everywhere. This is very nice. So therefore I get 2 is equal to cosine plus 2 cosine is 3 cosine. So the cosine of theta is 2/3. I immediately have my answer because h is r times the cosine, which is the 2/3. That's the answer. The height is 2/3 r, isn't that nice? Doesn't matter how much mass the child has. It doesn't matter what planet the child is on. And it doesn't matter, well, the angle doesn't matter about the radius, but the height will, of course, be determined by the radius. It's 2/3 times radius. I'm just curious, figure out what that angle is. We can do that very easily by taking the arc cosine, and we get 48.19 degrees. Nice. Now let's go ahead and find what the velocity is that the child goes off. So I guess we could say in the given, it'd be nice to say what is this and what is the velocity. And this is when you leave the ice. When leaving the ice. It's always good to show in the beginning with the diagram or sketch and what the problem is and what all the givens are. So let's do that. And then here, what's the easiest equation I can go to figure this out? I think that the easiest equation here is probably this one right here. This one right here. The m's go out and I get g cosine of theta is equal to v squared over r. And I know that the cosine is 2/3. So that means v squared is 2/3. I bring the r over here, I have gr. The cosine's my 2/3, and I bring the r over with the g. And the velocity is the square root 2gr over 3. Nice. Nice, elegant problem. I wanted to get an idea of some numbers here, so what I did is I went ahead and picked r is 1.25. And if I were making this problem for students, I probably would go ahead and do this. I want to keep everybody happy, and engineers like numbers. practical application, and I do too. So we put down, here's some numbers, and if we do this, R is 1.25 meters, then we could go ahead and work this out, and we get for the velocity, when you plug in the 9.8 for the G, and the R, this value, you get 2.86 meters per second, which is about 10 kilometers an hour, or close to 6.5 miles per hour.